we really open up new worlds. And then perhaps the biggest surprise was that we realized that unlike other fields, even ones where you would think you would need to speak across disciplines, that we had successfully accomplished communication across disciplines because of the way nanoscience came together from chemistry, physics, biology, math, engineering, toxicology, medicine, and so forth. And so there was an impetus on us to apply our skills into other fields. Again, a different story, but I'll encourage you to read these pieces about those ideas. Now, once upon a time, back when I was at IBM, as David mentioned, we realized that the scanning tunneling microscope was more than a structural measurement tool, and we were able to move atoms around. And I was the first one to do that. It was before my postdoctoral mentor, Don Eigler, learned to spell. I just wanted to find out what was underneath the atoms. So I reprogrammed the microscope so I could slide them out of the way. And then many of you become familiar with the atomic corral, and you probably don't know Newton's cradle because we never published it, that Erhard Schweitzer did in the laboratory there. To me, the most important STM image ever recorded was this one. It's actually a pair of images superimposed of the stoichiometric gallium arsenide 110 surface. Now I teach first year undergraduate chemistry, so I have to start off saying arsenic's to the right on the periodic table, and so it's more electronegative. So there's a charge transfer from the gallium atoms to the arsenic atoms. Thus, when we look at the filled atoms on the surface, by filled orbitals on the surface, by having electrons tunnel out to the tip, we image the arsenic atoms, and when we tunnel in, we image the empty states on the gallium atoms. And what that made us realize is that we could put on goggles, essentially, with the STM and look at a surface the way an atom or part of a molecule might. Think electrophilicity, nucleophilicity. It's more complicated than that in terms of the atomically resolved spectral imaging that we can do, but we and others have developed a series of spectroscopic tools that have allowed us to probe the surface to understand the electronic, chemical, physical, spin, and other properties. And that, I think, is really a key to what we're going to talk about today. Now, the other bit of motivation comes as follows. These amazing two-dimensional materials have been developed over the last several years, and we'll take the prototypical example, graphene. Now, because of its perfect conjugation and its idealized semi-infinite form, there are amazing optical, mechanical, electronic, and other properties, but how we make contacts to it remains just highly problematic. In one case, right, we evaporate metals over the top of it and destroy its properties that way. In another common strategy, we oxidize it, breaking the conjugation, ruining the properties, and then reduce it back a little bit to make a chemical connection. And so my argument from what you heard on the first slide is that we should use a century of organic chemistry to be able to make the targeted carbon-carbon and carbon other atom bonds that we want, such that the contacts that we make to smaller pieces of graphene nanoribbons have optimized electronic or other properties. And we're able to probe those contacts because we can use the scanning tunneling microscope to measure the molecular orbitals, to measure their continuity, and to measure their spectra. That translates over to other materials as well. If you take metal chalcogenides, one can swap out the sulfur, selenium, for instance, with not just an alkane thiol, as Taki Lee at Seoul National University did here for passivation, but we could attach a molecule that would give us the connectivity and the contact of the kind that David and I and many others have been working on for many years. And I'll give you examples of what we're trying to do there. But I'll warn you, there isn't a punchline to this talk. I'm excited to be working on it, but we're not all the way there yet. Okay, now, some time ago when we first started looking at the conductance of individual molecules, pairs, lines, and clusters, we developed this strategy of isolating the molecules right along structural domain boundaries and self-assembled monolayers. And again, the subject of another talk is all the problems with these monolayers because the molecules can conformationally relax, are tilted, and thus have domain boundaries and so forth. We took advantage of those defects for isolating the molecules and then positioned our STM tip over the functional part of the system to understand how the molecules functioned in the cases of switches and motors, for instance. And one of the things that we discovered in this system, the ligophenylene ethinolenes, is that the way that the molecules switched was that there was a conductance change when the hybridization of this buried bond changed. So just like in semiconductors, the contacts were everything. And we developed a series of tools to study those systems, such as measuring the largest buried dipoles in the system so as to measure the tilt angles of these molecules and probe the buried bonds. We could measure the microwave conductance of the molecule substrate system, which would vary according to how connected the molecules were to the substrate. And thus we had a way to measure the conductance of the buried bond. And we'll apply those same ideas in the systems that we're now studying. Now let's get on to the graphene nanoribbons for a bit. And this is the work of Patrick Hahn, who ran a laboratory for us at Tohoku University in Sendai as part of this WPI Center, the Advanced Institute for Materials Research. And Patrick's interests were in chiral graphene nanoribbons. And the reason for that is that the armchair and the zigzag nanoribbons had been studied for some time, but no one had access to these chiral systems that we thought we knew we could make, and we wanted to probe their spin and other properties. For a background, you probably know that instead of having no band gap for the semi-metal, semi-infinite graphene, when you make the armchair graphene nanoribbons, you open up a band gap, and the size of that gap depends on the width of the graphene nanoribbon. The zigzag graphene nanoribbons have interesting spin properties at their edges. And so Patrick took what we had known, we've been working for 25 years on the Ullmann coupling reaction that's used to bring together haloaromatics to form larger aromatics on surfaces, particularly copper, but can be done on other surfaces as well. And so Patrick designed the precursors that he knew would assemble on the surface through substrate-mediated interactions, which he had also studied with us. And then when the intermediates were zipped together, he expected to get these chiral structures, which he did. And that's very much along the lines of what Klaus Mühlen has done, designing interesting precursors for these graphene nanoribbons. The reason we use copper is that it's so strongly interacting with aromatics. You can see that silver and gold have aromatics sitting much higher off the surface and interact much less strongly. And it was known back in the early 20th century that copper catalyzed this reaction. Okay. And so what we're able to do is image the reactants, the intermediates, and the products by first depositing the molecules, then raising the temperature up to the point where the halogens are cleaved off, cooling back down and measuring, and then raising the temperature up to where the intermediates react, very much like the arrow pushing we learned in early organic chemistry. We get to see the result on the surface. And indeed, as Patrick predicted, along different growth directions, we would get different chiralities. We don't have a color STM, he just color coded which way these were going. And we saw alternating left, right, according to the growth direction on the surface. A former postdoc from the laboratory, Nacho Pascal, in San Sebastian then took a vicinal surface where all the terraces have the same orientation. And in that way, he was able to make single chirality structures across the entire surface in a really beautiful set of experiments he did at Nanogune. We can go and measure the electronic properties of these nanoribbons. We can resolve them with atomic resolution. We can slide a halogen atom up to the edge of the nanoribbon to quench the surface state and divide what's essentially a particle in a box into two particles in two boxes in the molecular orbitals. And we're able to measure all these systems in that way. Now, someone wrote a comment about our paper saying that under different conditions, they measured different products, and thus our mechanism must be wrong. And we took that comment seriously, And we wanted to understand why it is that they got a different product, although it wasn't terribly surprising that one might get a different product under different reaction conditions. And so when we went to the higher temperatures and the higher coverages, indeed we saw these different products, but because we had higher resolution imaging capabilities, we were able to show that the mechanism that we discussed was still correct. But what got me particularly excited about these images were the junctions. And these junctions are contacts. And so we said, well, let's go explore their electronic properties in detail. So we went and we did that. Now, those of you who know me and what I did over the years know that I have PTSD about phase. And so not only do we measure the topography in the STM, but we measure the phase of the molecular orbitals, because a contact with a node in it is a terrible contact, and we need to know whether there's a node or not. And so in the straight nanoribbons, no nodes, but you would think, well, you can't really make devices that just keep going in the same direction forever. And so we looked at these other angle junctions, and this one in topography, you might have said, well, that looks pretty good. But when you look at what's called differential conductance, and thus the phase of the orbital, you see nodes. These stripes, right, are many nodes. That's the kind of thing that gives me nightmares. And so then the question is, how do you put together these systems such that they don't have nodes? And the strategy, not yet elaborated, is to prepare a variety of precursors, to put them down on the surface at the same time and make a combinatorial set of contacts, and then explore those experimentally, and then tie in theory to do measurements that help us predict what contacts we'd ultimately like. In the meantime, we've also learned we and others have learned to functionalize the edges of nanoribbons. Here we have them functionalized with sulfur on the edges. We can make both the cis and the trans forms. And it turns out that the band gap only depends upon the length in these systems, independent of where the placement of the sulfur atoms are in each case. Our colleagues at UCLA have made these interesting side functionalized graphene nanoribbons, and one of our other editors at ACS Nano, Andrew Wee, has also made these nitrogen edge functionalized nanoribbons. And this has become something that we can now further explore as a way to put in a band gap, control the contact properties, and so forth. And so this chemistry is still being developed in real time as we speak. The Berkeley group did something very clever. They took advantage of that linear variation in making quote unquote devices. So here what they did, this is Mike Crummey and Felix Fischer and the theory cohort there, took graphene nanoribbon in which there was a change in the width so as to change the band gap. And then they also made this zigzag structure in which the side group functionality was different on the two sides, and thus the electronic properties are varied. So maybe even in the case of these linear systems, there are going to be ways to control the electronic properties. I'll change gears for a moment, and then we'll come back. And that is, remember I alluded to the problems of the alkane thiol self-sum monolayers. Because those linear chains are flexible and because they tilt, there are all kinds of defects that are intrinsic to those films. And so we started to ask, how could we eliminate those defects and make more perfect films? And in fact, what we were interested in initially were more perfect domain boundaries, but we got to this point where we realized that if we eliminated tilt, we eliminated tilt boundaries. And if we eliminated flexibility in the backbone, then we eliminated conformational relaxation. And so we came upon a set of molecules that stand upright on the surface and are made of rigid cages. Our favorites at the moment are these Carburine cages. These have boron in all the green positions and 2 carbon atoms. There's a hydrogen that I'm not showing on each atom here, other than that one, where there's a sulfur attached for the surface linkage. And because the carbons here are hexacoordinate, unlike what we teach in high school chemistry. They are behaving like boron with multi-center bonds. They're electron deficient. And all of the isomers of these molecules can be synthesized. There was an enormous effort in the Soviet Union and another one in the United States during the Cold War, and a bunch of money poured into these for funny reasons. And so they can even be scaled up to the ton scale. And so according to where we put the carbon atoms, that determines the surface charge. And because all cages and all isomers form identical structures on the surface, we can also mix them, and we can also test the variation of properties without changing the structures. So in this case, the carbons are essentially sideways, and one ends up with a nonpolar surface. Here the carbons are up, and one ends up with a positively charged surface. When we put the carbons down, we end up with a negatively charged surface. And we can see that at the nanoscale, and we can see that at the macro scale. A postdoc in my group, Jay Kim, realized that we could use that to get band alignment for organic electronics. So normally what one does is one has a contact, and then one has the active organic layer, but needs to match up where the electronic states are. And so people like Seth Martyr at Georgia Tech fluorinate a polymer to tune the band alignment. But you know, when you fluorinate a polymer, you're essentially making Teflon, and you have to worry about changing the wetting properties and thus the morphology of the active layer. And so what Jay did was he mixed these two different carburines, and he did this for both gold and silver surfaces, and showed that he could tune the bands on the surface by over 1 electron volt. Each one of these points is 40 devices. He was able to get perfect band alignment. He was able to show he didn't change the wetting properties, and he didn't change the morphology. And I thought that was a really neat application of this work. Let me finish up by talking about spin, and we'll pull a bunch of this together. You had a whole session on that earlier today. The chirality-induced spin selectivity effect was discovered by Ron Nauman a few years ago. Yossi Peltiel and Abe Nitzan, a bunch of others, including our group, have looked to explore this field. People like my colleague, a little bit of background, a little bit of light music would be nice now, I guess. Have looked at whether there might be such spin effects as quantum effects in biology, and we've had a great deal of fun and excitement working with her. There are opportunities in spintronics that I'll mention in the last couple of slides. My favorite, and I think most compelling experiment in this field was one that Ron did with Bert Mayer, where he showed that in water splitting, the side reaction of producing peroxide is turned on and off, right? A lot of people have argued about quantifying this effect and what the spin filtering and transport are. This is really an experiment that nailed whether we can see the effects of spin or not. And then in my own group, what we've done is set up very large numbers of parallel experiments where we work with either fluorescence or synchrotron studies or electrochemistry, and look at a wide variety of systems, DNA, proteins, synthetic systems, to look at the effect and to quantify it with a statistical significance. And one of the more interesting things coming along is our partner at the Czech Academy of Sciences, Tomas Baza, has been able to prepare chiral carburines now and to separate them in quantity. So now we'll be able to get a very high quality chiral monolayer. We'll be able to pattern, as we did with the DNA and the other systems, to do side-by-side comparisons of the two enantiomers as well as control experiments, all on the same surface. And one of the beauties of the carburines is that they can be further functionalized, and so that we can use those as contacts. We can attach them, for instance, to transition metal chalcogenides to serve as those contacts that I showed you early in the talk. And so I would say stay tuned for a lot of interesting, very high quality systems where we combine chemistry and material science and physics and engineering to optimize spin contacts too. Okay, so because we were able to gain the ability to see these surfaces, we learned how to isolate individual molecules. We learned how to prepare very high quality monolayers. We learned how to pattern. And this, I just can't overemphasize the importance of this tool development and the ability to turn on different measurements contextually to understand contacts. And I hope that that, in collaboration with the chemistry, physics, materials communities, allows us to target these perfect contacts. And I think there's a role to play for many of the attendees at the conference in this area. If you're interested, I tried to put everyone's name on every slide as I went along. Here are the collaborators around the world, and then the people who paid for this, particularly Department of Energy, NSF, and the Keck and Kavli foundations. And so with that, I'll stop and look forward to the discussion. And again, thank you for including me in this conference. I'm sorry I couldn't be there in person, but I'm hoping in the next few months, the vaccines kick in and we can all see each other live and in person again in our travels around the world. Thanks very much.
Thank you very much. And the talk is open for questions. We'll left some time. So I haven't seen any questions in the Q&A. So if there's anyone who has a question and wants to place it now, otherwise I'll go first. But I'll wait 30 seconds. That's fair.
Can I ask a question?
Yes, Mr. Cohen.
You mentioned very briefly that when you had all those, various networks and they were kinked, then they weren't conducting there, and you use these combinatorial techniques and other methods to move things around. Can you elaborate a little bit on that?
Sure.
How you actually make conducting connections?
Yes. So for instance, we can make hexagonal tiles where the edges are functionalized differently, or where we have an offset either dopant atom or vacancy. And then according to the orientation of the tiles, when they come together, we're able to measure the properties of the junction. Those also build up into rather large mats on the surface. There was a nice experiment that Roman Fezel did with some of Klaus Mühlen's molecules showing the tiles, but not doing the combinatorial variations on the surface at the same time. So those kinds of experiments let us do many measurements all at the same time, both for exploring what would be a good contact, but then also feeding in critical tests for theory. So in our theory collaborations, we tend not to jump on a horse and say this is the way to go, but rather to constrain the results strongly so that we can tell who's getting it right with what method.
Okay. Yes, Ernesto.
Ernesto, congratulations. Hi.
So you're on the Red Sea. The Dead Sea.
Dead Sea, yes.
Okay.
I'm thinking floating and warmth.
I was wondering when you showed these chiral graphene nanoribbons that are sitting on the copper. Is it possible to measure transport across these ribbons when they are in such a strong contact with the conducting substrate?
Excellent question. Yeah, so it would be possible, but probably not so useful as you kind of point out. And so what other groups have done, and we have discussed but haven't done yet, is to build a nitride or other insulating layers on top of the metal surface. In some cases, the catalytic effect continues across those layers, but it gives you an insulating barrier that then lets you do the kind of experiments that you're describing. So actually, we sent Patrick to the late Wayne Gooden's lab for a year to learn that process. but that didn't end up getting so far. People like Andreas Heinrich, who used to be, he was my, many generations later successor at IBM and moved to AHWA in Seoul now. He's done some interesting experiments like that, not with Ullmann coupling reaction, but with spin related measurements on surfaces. So one can build that insulator in, and ultimately you might want to remove these ribbons as well. And I think there are ways to do that, but we have not.
Thank you.
Mark?
Thank you. Thank you very much, Paul, for a great, wonderful talk. And my question is about the monolayers of Carburine. First, you mentioned that you eliminated two of the molecules. Could you please comment on this? And also, the second question is, how does the fact that they do not have a long carbon backbone negatively affects their stability compared to usual monolayers, which we know?
Okay, so you have a couple of assumptions built in there, right? So it turns out the carburines are quite stable. Turns out more than they'll last on the surface in thermal absorption up to higher temperatures than comparable alkane thiol that we could work on. You end up with a much more perfect monolayer. Essentially, the only defects that one sees in a complete monolayer there are phase offsets of the registry that are either translational or rotational. You can also build in dipole-dipole interactions where as long as the dipole isn't normal to the surface, and that contributes to the stability. Now, at the other end of the spectrum, adamantane thiols, which are also upright cages, have minimized contacts between the molecules, and their surface attachment density, that sulfur gold bond, is reduced by about a factor 1.8. So those are actually quite labile, and one can use that to advantage to put them as a sacrificial layer down for chemical patterning. So for instance, with microcontact printing, one takes a patterned rubber stamp with the thiols inked, puts it down on the surface to transfer the molecules. But if you work on a blank surface, then the molecules start to diffuse. And you can see that in electron microscopy and other imaging techniques as sort of ghosts around the patterns that are made. But if we start with the labile adamantane thiol layer, then we can pattern right on top of those and displace the molecules wherever the stamp is patterned, but prevent diffusion. And so there are a bunch of advantages we can use with the cage molecules in those circumstances. But the carburine monolayers are actually quite robust, and you gain a benefit from the lack of flexibility, and one can do quite a bit in terms of manipulating stability. So for instance, you can change the valence of attachment. You can go to a dithiol and then double the strength of the attachment in that way for the dithio carburines, as long as the sulfur is on the same end of the molecule.
Thank you.
Sure. Yeah, they're really, I'm amazed it took us 15 years to figure out that we should be using those. It's a little bit embarrassing, to be honest, that we didn't realize that we could make our lives so much easier through symmetry.
Thank you. Are there further questions? At the moment, I don't see any from the attendees. So I have a question, and in the work with the chiral molecules and any molecules actually, is there a way in your measurements to quantify the coupling strength of the molecule to the surface, to the substrate, and you do your electrical measurements?
Yeah. So
what are the energies involved in the different chiralities?
Yeah. Yeah. So that's certainly one of the key questions. And so we're hoping that the combination of tools we've developed for measuring the buried contact will be of use there. And in addition, what we'll try and do is add and flip magnetic fields. I passed over very quickly, but Eric Fullerton at UCSD has prepared these substrates for us where we can flip the magnetic field in the identical system and do measurements that way. So combining our, and we haven't done it yet, combining our measurements of the buried conductance with those measurements we hope is going to help us start to pull out what that coupling is.
Yeah, because it would be an ideal system to
Agreed.
get the relative energies that are involved.
Yeah, I agree. And the carburines are a great one for that because they're so well behaved. We don't have the molecules yet because the labs are shut in Prague. But just before they closed, Tomas figured out how to how to do the separation. He'd gotten 2 milligrams by brute force, and now he can get a lot.
Okay, thank you. Are there any further questions? This is your chance.
Oh, I think there's a question in the chat.
Ah, okay. I didn't see that. Yes, from Avad Shalabni. So I'll read it, or you want to read it?
I can read it, I guess. Thank you for this nice talk. My question is about the STM measurement. The STM tip can tilt the sand layer. How can you neutralize this effect and define the defects? So one of the things that we do in our STM measurements is we vary the distance of the probe tip from the film. And we can tell when we're penetrating the film, for instance, that's the point at which we lose resolution of the lattice and we see other effects. And we can also tell if we're perturbing or not by doing measurements over a range of tip sample separations. So you're correct that we can go in and we can scrape through defects. And in the past, when we looked at the molecular switches, we were able to make them change from one state to another when we were in very perturbative conditions. But when we're further away and out at low current ranges, then we didn't see any such perturbations. Yeah, it's part of the neat aspect of the STM is that you're able to tune the interaction strength of the tip with the sample that you're studying.
I see that Sydney, you had a question here. It's on the chat.
That was the one that I asked verbally. So
And everything has been answered. Okay, fine. So then, since we have only a few minutes left, I think that if there are no further questions, I want to thank you very much for a very illuminating talk. And
Thank you
see
so
you
much
soon.
for having me. Everyone enjoy lighting the candles tonight and Hanukkah. And again, I look forward to seeing you in person. Thanks so much, everybody.
Thank you, Paul.
thank you very much.
Thank you.
Bye.
Thank you.
Bye.
Thank you
Thank
very
you.
much.
Bye.
Bye-bye.
Okay, and now we